Hello everybody, I am Lup from sunny Singapore. Over the past 7 months, we did many fun, cool things with Apache NuttX RTOS on Ox64 BL808 RISC-V single board computer. I shall explain everything in this presentation. If you would like to download the presentation slides, please head over to this link, lapyuan.github.io/NuttX. That's the letter L, not the digit 1. My presentation, transcript, articles, and source code are available at that link. Yet we had endless hours of fun over the past 7 months with NuttX on Ox64 SBC. In this presentation, we begin with the porting of NuttX to Ox64. Interesting things we saw in memory management, interrupt controller, and NuttX apps for Ox64. Then we created an emulator for Ox64 that will boot NuttX, which is super helpful for automated daily testing, also for automated log analysis. Finally, we go wild with NuttX on Ox64, stretch it to the limit, do all kinds of things in NIM, JavaScript, drag and drop apps, tiny C compiler. Some folks watching this might be receiving Ox64 boards. To install NuttX on your Ox64 SBC, please follow the instructions here. If this link is too long to type, just browse to hexter.io/lapyuan and you will find the Ox64 article there. Remember, this is the letter L, not the digit 1. What is this BL808? BL808 SoC is a curiously complex creature with 3 asymmetric RISC-V cores. One 64-bit core based on T-head C906. This is the multimedia core with BP, CSI, and DSI, and neural processing unit. NuttX runs here. One 32-bit core based on T-head E907. That's the wireless peripheral core with Wi-Fi, Bluetooth LE, Zigbee, audio, USB, and Ethernet. NuttX doesn't run here yet. But we don't touch this. The 32-bit low power core based on T-head E902. Today we shall talk about the Ox64 single board computer by Pine64, which is the development board for the BL808C SoC. BL808C supports MIPI CSI cameras, but not MIPI DSI displays. We could potentially connect a MIPI camera module to Ox64 and turn it into a security camera. Here is a demo of NuttX on Ox64 single board computer. Ox64 boots NuttX on a micro SD card thanks to the U-Boot bootloader. Ox64 has plenty of RAM, 64 MB. That is why we can run a JavaScript interpreter on Ox64. Here is our JavaScript that blinks the LED by calling the NuttX POSIX API. When we run it, yep, it blinks the LED. Later in the presentation, we shall explain how we ported the Quick.js JavaScript engine to NuttX. Porting NuttX to Ox64 was surprisingly straightforward. We took NuttX for Star64 RISC-V SBC, made a few tweaks, and it runs on Ox64 SBC. Here is a helpful tip for porting NuttX to a new RISC-V device. Inside the NuttX boot code, we can insert RISC-V assembly like this. It prints something to the UART serial port, so we know if NuttX is built in on this device. And this works without fixing the memory map or kernel loading address because all this RISC-V assembly code is independent of memory address. This printing will always work regardless of the RISC-V device, assuming we have the correct UART base address. We did the same for porting NuttX to TinyEmu emulator. Check out the presentation here. Next comes the UART driver for NuttX, which is harder to port to new devices, especially for SoCs with special UART controllers like BL808. Here is a quick hack to make the UART driver work. We took NuttX from Star64 G8710, which still runs on the 16550 UART driver. We patched the UART driver so that it writes to the BL808 UART output register. With this quick hack, our NuttX UART driver will print boot logs and crash dumps to BL808 UART output, buying us some time to port the entire BL808 UART driver. One last thing we do to boot NuttX on Ox64 SBC, we update the system memory map and the NuttX build configuration. The boot address 5020 hex comes from U-boot bootloader. We are looking at the memory management unit of the Ox64 SBC, visualized as an animation. What exactly is this memory management unit? Memory management unit, or MMU, is the hardware inside our single-board computer that does two things. Memory protection. MMU prevents applications and kernel from meddling with things in system memory that are not supposed to. Virtual memory. MMU allows applications to access chunks of imaginary memory at exotic addresses like 8000 hex. But in reality, the system RAM recycled from boring old addresses like 5060 hex. Inside Ox64 SBC is the SV39 Memory Management Unit. We call it SV39 because SV is the name of the official RISC-V extension for supervisor mode virtual memory. 39 because it supports 39 bits for virtual addresses. If you can't remember SV39, just remember 3 levels of page addresses, each level adding 9 address bits. So we have a level 1 page table, which points to level 2 page table, and maybe level 3 page tables. Here we have the bits to indicate if the page table entry is valid, whether it points to read-write or read-only memory. If the G bit is set, it means this chunk of memory is mapped across all memory spaces. Then we have the physical page number, pointing to the actual chunk of memory. This is how we map the interrupt controller for Ox64 with a level 2 page table. Do we use level 3 page tables in NuttX? Yep. This is the level 3 page table for kernel code. That's why the execute bit is enabled. Here we see level 1, which points to level 2, which points to level 3, which points to the executable kernel code. This looks tedious and confusing, but we had to trace through the page tables to troubleshoot some memory management problems in Ox64 SBC. We talked about NuttX kernel. What about NuttX apps? Here is the level 3 page table for a NuttX app. It points to the virtual memory for the executable code of a NuttX app. The U bit is enabled, which means this chunk of memory is accessible in RISC-V user mode. To learn more about the RISC-V page tables, check out my article here. Okay, thanks, but why are we learning all of this? Well, we had to troubleshoot some really strange memory issues like this. GetPrime app runs okay on NuttX. After that, we run the Hello app, but it crashes with a page fault, which is totally weird because 8020 is a valid address for NuttX apps. Why is this happening? First, we need to understand that inside our RISC-V machine, there is an SATP register for supervisor address translation and protection. The SATP register points to the currently effective page tables for kernel and apps, and the SATP register gets swapped when we switch between kernel and apps. Is there a problem with the SATP register swapping, causing our Hello app to crash? We found the answer by inspecting the Linux kernel source code for Ox64. Remember that Ox64 runs on the BL808 SoC, which uses the THC906 CPU. But THC906 uses special RISC-V instructions to flush the memory cache. Thus, we call these magical RISC-V instructions whenever we swap memory spaces between apps. And it works, no more crashing. That was pretty scary, hitting strange new RISC-V instructions never seen before in NuttX. There's another thing unusual about the THC906 CPU. You know how when we press a key and it triggers an interrupt for your input? This is how we normally handle the interrupts for your input. We program this with the PLIC, Platform Level Interrupt Controller, which is a standard interrupt controller for RISC-V. But Ox64 and THC906 CPU works a little differently when we write to the PLIC interrupt controller. The writes get mashed up, leaking over to adjacent interrupt registers. The interrupt registers won't tell us which interrupt was fired, which gets super frustrating. So I walked to the beach, pondered my life choices, and suddenly I realized, what if we are not reading and writing our I/O memory correctly? Now, this problem doesn't happen before we enable memory management. It only happens after we enable memory management. Something to do with the page tables and the memory management unit. Again, we check the Linux kernel source code, how they configure the page tables for Ox64, and we discover a special bit for strong ordering. We must enable the strong order bit inside the page table entry so that reads and writes will be executed in the correct sequence. Again, this is a special feature specific to THC906 CPU. Everything works great in NuttX for Ox64 right after we enable the strong ordering bit. For NuttX on 32-bit devices, most of us use NuttX flat mode. This means that NuttX apps are statically linked into the NuttX kernel. For NuttX on 64-bit devices like Ox64 SBC, things get more exciting and complicated. NuttX apps are actually compiled into ELF files like this Hello World app. And NuttX apps on Ox64 are relocatable. See this call to the puts function? The address of the function will be filled in by the NuttX ELF loader when it loads our NuttX app for execution. This is good to explore in detail as we figure out how to bundle NuttX apps into the Ox64 image. Also, we will revisit this when we run TinyC compiler to compile NuttX apps. Back to our puts function. Our app will print something to the console, but NuttX apps can't write directly to the serial device, right? Nope, that is because NuttX apps run in RISC-V user mode. NuttX app can't access the serial device, which is controlled by NuttX kernel. That's why our puts function should eventually trigger a system call to the NuttX kernel, jumping from RISC-V user mode to supervisor mode. This is what we see when we enable system logging for NuttX system calls. How exactly does a NuttX app make a system call to print to the output console? Will NuttX apps require some special code to make system calls? Nope, not at all. The system call is totally transparent to our app. Our NuttX app will call a normal function named write that pretends to be the actual write function in NuttX kernel. It works by forwarding the write function call and passing the parameters to a RISC-V system call like the syscall3 function here. What's inside the syscall3 function? Syscall3 makes a system call to NuttX kernel with 3 parameters by calling the special RISC-V instruction, eCall. Later, we'll generate this system call with TinyC compiler, and we'll hit some very interesting problems. That is why we are going so deep into NuttX apps and system calls. We said that NuttX apps are individual ELF files. Where do they live? Well, they are bundled into a ROM FS file system. We call it the initial RAM disk or initial RD to follow the Linux terminology for bootable file systems. We started by loading NuttX kernel and initial RAM disk separately into RAM, but it became a hassle for U-boot bootloader. Thus, we just appended the initial RAM disk to the end of the NuttX kernel. U-boot bootloader will load everything into RAM, NuttX kernel, and NuttX apps. NuttX kernel will then search our RAM for the ROM FS file system, because the ROM FS file system has a magic number, and copy it into the designated memory region for mounting. That's how NuttX kernel accesses the NuttX apps. We trace through and figure out how NuttX kernel boots on Ox64 SBC. Check out the entire process in this article here. And this is how NuttX kernel starts a NuttX app on Ox64 SBC. Remember, the steps are more complicated because you're running in NuttX kernel mode instead of NuttX flat mode. Check out the details here. How were we able to accomplish so much over 7 months with NIM, JavaScript, TinyC compiler, all running on Ox64? Wouldn't it take us a lot of time to port and test the new NuttX drivers and apps? Well, we became super productive because we created a software emulator for Ox64 SBC, and it boots NuttX. We took TinyEmu emulator and create an emulator for Ox64 SBC. Ox64 Emulator runs at the command line and inside our web browser, thanks to WebAssembly. Today, we run it daily for automated testing, which is triggered by GitHub Actions. Ox64 Emulator makes it really quick to test and experiment with new NuttX drivers and apps. We have another presentation on the TinyEmu emulator for Ox64 SBC. Please check out the presentation at this link. We are looking at the emulator for Ox64 SBC running inside a web browser, though it runs okay at the command line too. We see that NuttX boots perfectly on our Ox64 emulator. This is NuttX compiled for Ox64 without any changes. This works because we customized the TinyEmu emulator to emulate the Ox64 memory map, UART controller, and GPIO controller. For details, check out our presentation on TinyEmu emulator. It's already 2024. NuttX is running on single-board computers with plenty of RAM, like Ox64 with 64 MB of RAM. Can we make good use of the extra RAM, like for creating memory-safe apps for NuttX? NIM is a newish programming language that has garbage collection and reference counting, so it works better when there's extra RAM. This is how we blink an LED in NIM. We call NuttX to open the LED device, call iocto to flip the LED on or off, call uSleep to wait a while. And here is the loop that repeats the entire process. NIM looks similar to Python, so NIM is good for folks who are familiar with Python. How will NIM know about open, close, iocto, uSleep? This is how we import the NuttX functions from C into nim. Notice that nim imports C functions directly from C header files. This works because nim programs compile into C code, which gets compiled and linked into NuttX with the exact same GCC compiler. This means we get seamless integration between nim and NuttX. NuttX is officially supported by nim, thanks to the nim community. And today, nim is also supported by NuttX. So go ahead and check it out here. We have plenty of RAM on NuttX now. Guess what also needs plenty of RAM? JavaScript. Quick.js is probably the tiniest JavaScript engine, and it supports POSIX functions. Lots of fun possibilities with NuttX. We might use Quick.js for interactive, iterative experiments on NuttX. Yep, Quick.js runs okay on NuttX for Ox64, and we can blink the LED in only 4 lines of JavaScript. We open the LED device, then call iocto to flip the LED on and off. Here is our JavaScript that blinks the LED by calling the NuttX POSIX API. When we run it, yep, it blinks the LED. Later in the presentation, we shall explain how we ported the Quick.js JavaScript engine to NuttX. The really awesome thing about Quick.js is that it supports POSIX functions. So it is a perfect fit for NuttX. But iocto is missing from Quick.js, probably because it's too platform specific. Thus, we added iocto to Quick.js with a few lines of C code. Do we just compile Quick.js for NuttX and expect it to work? Nope. Remember that NuttX was created for tiny microcontrollers. Some of the NuttX defaults are really tiny. Feels a bit like micromanagement, and here's why. We compiled Quick.js for NuttX with nearly 0 changes, but when we run it, it crashes with this crash dump. And this is a strangely loopy crash dump. It loops on and on and on forever. Took us a while to figure out, but NuttX ran out of stack space. We increased the NuttX app stack space from 8 kilobytes to 64 kilobytes, and Quick.js runs okay. No more loopy crash dump. Then we noticed that the Quick.js ELF executable was huge. The ELF executable was 22 megabytes. By default, NuttX apps are partially linked and relocatable. Most of the 22 megabytes is filled with relocatable symbols. Hence, we converted the NuttX app from partially linked to fully linked, which reduced our app size from 22 megs to 4 meg, and it loads a lot quicker on Ox64, since the NuttX ELF loader doesn't need to fix up the relocatable symbols. How small exactly is Quick.js? Will it run on smaller microcontrollers? Because a JavaScript engine with POSIX sounds really helpful for NuttX. We generated the linker map for Quick.js and we ran this visualization tool, linker map viz. We discovered that Quick.js with all the toppings needs 550 kilobytes of code and data. What about heap usage for Quick.js? We turned on heap tracing in NuttX, which is actually called memory management under the logging option. We captured the heap logs, imported into a Google spreadsheet, and monitored the heap allocation over time. Barebones Quick.js uses 280 kilobytes of heap space, since JavaScript depends heavily on dynamic runtime memory for managing JavaScript objects. That's 780 kilobytes for code, data, and heap. Quick.js with all the fixings, it uses 370 kilobytes of heap space. That's nearly 1 megabyte for code, data, and heap. So yeah, if we have a supersized NuttX device like Ox64 SBC, Quick.js will run on NuttX. Remember our demo earlier with Quick.js running on Ox64 Emulator, blinking a simulated LED. How did we simulate the LED? We tweaked our Ox64 emulator based on TinyEmu to watch out for all writes to the GPL register of the BL808 SoC. Our emulator sends a notification to the web browser JavaScript so that it renders the simulated LED in HTML, flipping it on and off. Ox64 emulator becomes really helpful when we start emulating onboard peripherals like GPIO and LEDs. Now that we have JavaScript running on NuttX, what are the fun ways of creating JavaScript apps for NuttX? Maybe something drag and drop like Scratch? That is why we are hopping on to Blockly, the popular drag and drop toolkit for creating JavaScript apps. As a NuttX app developer, all we need to do is to drag and drop the blocks to create this visual program, and Blockly will emit this JavaScript code. We are looking at a demo of drag and drop apps for NuttX, powered by the Blockly Visual Programming Toolkit for JavaScript. Here we are dragging and dropping an app that blinks the LED by calling the NuttX POSIX API. At the left is the JavaScript code that is auto-generated for our visual program. We can run this on the Ox64 emulator. Our web browser JavaScript will automatically send NSH commands to transmit our visual program into the emulator. When it runs, Ox64 Emulator will blink the simulated LED. The same works on a real Ox64 SBC. Here we use the Web Serial API, which is supported by modern web browsers. Our web browser JavaScript transmits NSH commands and our visual program to Ox64 over the USB serial connection. QuickJS runs our program and blinks a real LED on Ox64. We have seen the drag and drop app builder for NuttX. Here are the internals. Our app builder generates a JavaScript program that will run on our Ox64 emulator in a web browser with WebAssembly. The same JavaScript program also runs on a real Ox64 single board computer. We use the Web Serial API that is available in most browsers to send NSH commands to Ox64 over the USB serial console. To blink an LED, we need to call POSIX functions in NuttX. That is why we added these POSIX blocks to Blockly: open, close, IOPTO, and sleep. For each POSIX block, we created the code generators that will emit the JavaScript code for the POSIX block: open, close, IOPTO, and sleep. Remember, we are running all this on QuickJS JavaScript Engine, which works great with these POSIX functions. How do we magically run the generated JavaScript on Ox64 SBC? In modern web browsers, we have the Web Serial API that will control any device that is accessible over the serial port. We use the Web Serial API to send NSH shell commands and QuickJS commands from the web browser to our Ox64 SBC. Our commands are transferred line by line, but remember that serial I/O is unreliable and might drop characters, so the data transfer is kind of slow right now. We might switch to Z modem. To control Ox64 SBC from a web browser, we click the Connect button, which will show a list of serial devices. We click Connect, and our JavaScript takes over, sending NSH and QuickJS commands to Ox64 SBC. Okay, JavaScript runs fine in a web browser, and JavaScript works okay with NuttX Emulator and real NuttX devices. What about plain old C? Can we let NuttX learners write NuttX apps in C, compile them inside a web browser, and run it in a NuttX emulator or a real NuttX device? Let us try it with the simplest C compiler, Tiny C Compiler or TCC, and run it inside a web browser with WebAssembly. At the left is a bare-bones NuttX app that will print something. We compile our NuttX app with the Tiny C Compiler, which produces a RISC-V ELF executable. Our web browser JavaScript copies the ELF executable to Ox64 Emulator, injected via the ROM-FS file system. And it works. Ox64 Emulator runs the compiled program, printing something to the NuttX console. We compiled Tiny C Compiler from C to WebAssembly thanks to ZIG Compiler, which calls CLang to convert C to WebAssembly. But there is a problem with WebAssembly. Tiny C Compiler was created as a command line app. It calls POSIX functions to open source files and to read them. And WebAssembly running in a web browser ain't no command line. We counted 72 POSIX functions needed by TCC compiler but missing from WebAssembly. Thus, we fill in the missing functions ourselves. Effectively, we're emulating POSIX in WebAssembly by writing our own ZIG functions. Now we have Tiny C Compiler running inside our web browser, and it compiles our NuttX app from C into a RISC-V ELF. Our JavaScript copies the RISC-V ELF into Ox64 Emulator, and it runs okay. Tiny C Compiler didn't seem to generate the correct RISC-V code for NuttX system calls. We tweaked the RISC-V code and made it work with system calls. Here comes another problem with Tiny C Compiler. We need C header files like stdio.h, but WebAssembly doesn't support file systems. We added a read-only file system to our WebAssembly, the ROM-FS file system, and we host the C header files inside the ROM-FS file system. We modified the code in our ZIG wrapper for TCC, emulating the POSIX file access functions by calling the ROM-FS file system. And how did we get the ROM-FS file system running inside WebAssembly and ZIG? Well, NuttX has a ROM-FS driver in C, so we ported the ROM-FS driver from C into ZIG. Our ZIG wrapper emulates POSIX file access for the Tiny C Compiler by calling the ROM-FS driver. Yep, we actually took a chunk of code from a real-time operating system and ran it inside a web browser. ZIG Compiler will compile the NuttX driver for ROM-FS with a few minor code changes. Then we can call the driver from ZIG WebAssembly. In ZIG, this is how we mount our ROM-FS file system, by calling the NuttX driver. The driver integrates really well with ZIG. The file system checks from NuttX are still in place. If the ROM-FS file system contains garbage, our ROM-FS driver will fail the mount operation because it searches for a magic number at the top of the file system. Also in ZIG, this is how we open and read a ROM-FS file. The NuttX driver for ROM-FS works great with ZIG inside a web browser. Next time we're thinking of using NuttX drivers outside of NuttX, just go ahead and try it. It might surprise you. While porting NuttX to Ox64 SBC, we wrote plenty of detailed notes. Check out the articles here. More articles here. Yep, we are looking at 7 months of detailed documentation. everything we know about Ox64 SBC. And these too. Remember, you can download these slides from this link, lutyuan.github.io/NuttX. That's the letter L, not the digit 1. We have 2 more presentations on Ox64 SBC, about the tiny emu emulator for Ox64 SBC, and the analysis of real-time logs from Ox64. Please check out the presentations at this link. Today we had so much fun with NuttX and Ox64 SBC. Porting NuttX to Ox64 was surprisingly quick, maybe because NuttX runs better on RISC-V SBCs. We created an Ox64 emulator that is super helpful for daily automated testing and regression testing. We saw today that NuttX is no longer a boring textual RTOS. NuttX really shines when we experiment with new things like NIM, JavaScript, drag and drop apps, even tiny C compiler in a web browser. Let us do many more wow things with NuttX. Thank you.